Okay, hello everyone, how are you? Hope you're enjoying all the talks and general hacking stuff today. I'm going to talk to you today about hunting quality and how we can apply kind of workflows and techniques and tools that are usually associated with traditional software development to the kind of security research that I myself have found myself doing. It's essentially just a collection of stories of stuff that I've done that I've thought, oh, that's something that other people might be able to benefit from. So, quick about me slide. Lots of people don't know me. If you've seen me before, yeah. I'm based in Singapore. I've been here for about three and a bit years, I think. I've been working for the last year at F-Secure, which until lately was, worked for MWR, and now we're F-Secure, and the branding switchover was last week, so if you catch me saying MWR instead of F-Secure, please shout. I have lots of experience. Most of my experience is in kind of fuzzing, binary exploitation. I like fuzzing things. I like writing exploits. I like kind of working at low levels, playing with the kernel, playing with electronics, that kind of thing. But the main reason I want to stress this is not because I want to show off or whatever, but because I want to make. I think there's a bit of a myth that people who are traditionally people who are very interested in low levels and hacking and that kind of thing aren't able to benefit from the high levels of traditional software development practices. So that's really why I say that. I just want to dispel that myth before it started. So a little bit about my role at Countercept, or F-Secure, and yeah, a bit about my current role. I'm a pure security researcher who supports a threat hunting team. So I don't do any threat hunting myself. I spend all my time doing research into usually the attacks that the threat hunters find. The threat hunters will go and research an attack, and then if it requires more time, more investment, I'll go and take a good in-depth look at it. As part of this role, I often find myself coordinating a lot with the different aspects of the company. So I'll talk to the software team when I want to push a detection out to our clients. I'll talk to the network people when I'm not sure about most things to do with networking, to be honest. So because of this, I've come into contact with a lot of different aspects of the way that things work, and I've kind of pulled out things that are useful to me as a security researcher. So what are we talking about today? I'm talking about one thing, and that's stability. In the technical sense, not in the like financial or mental state. Talking about stability in a software sense. I'm going to use three different areas to kind of highlight this and to show where I've really used it and where it's benefited me as a researcher. And the first one I'm going to talk about is in incident response tooling. And what I mean here is that if you're an incident responder and your client comes to you with a hard drive image and they say, okay, we suspect some badness on our system and we need to know what's going on. Obviously you need to be in a position to analyze that and find out, but if you drop that hard drive in your system and your imaging tool doesn't like a particularly new feature of NTFS, for example, then you're going to be in big trouble. You're in a very time-constrained environment. And we have our clients come to us with IR jobs, and the last thing we want to do is come back to them and say, oh, we can't do this yet because you're not on a supported version of Windows, so maybe upgrade and come back. That's not going to work. Likewise, if your tooling as well, when you write scripts for doing your incident response or that kind of thing, you need to get a good level of assurance that you can apply those to any situation you're likely to encounter. I'll talk a little bit more about that later. I do have some anecdotal examples of this, and unfortunately I can't share them because the incident response people were a bit, not at my current company, I'd like to say. The incident response people who I talked to were not keen on me sharing tales of their misfortunes. The best I could find is when I was Googling I found this post on Reddit just on their data forensics sub. And this was some poor soul who had a hardware write blocker. They've taken the SSD they've acquired from their client and they plugged it in and it doesn't work. And they're like, oh, what do we do now? We're a bit stuck. And obviously this isn't something that every business can, or that every scenario can prepare for. If you're an IR company, you're going to see lots of weird hardware. But if you're an incident responder who is in one particular company, if you can send your network admin people a quick email and find back a relatively general list of hard drives, send it off to your tool vendor, make sure there's no weird incompatibilities. I guess the big one is, the big example that springs to mind is if someone comes in with an M2 SSD or an NVMe like PCIe device, do you have a box you can drop it in? Can you safely analyze it? I don't know what the end of this story was because there was no response from this poster, but there definitely was not a happy ending that involved the right blocker. The top rated post was just like, oh yeah, well, ho-hum, can't do that. The second example I'm going to talk about, which I think is where there's the most room for, I say room for improvement, there's a lot of opportunity for us to adopt some of these technologies, is in how we do attacks and how we can do stable and reliable attacks. And it's kind of difficult in some degrees to justify a lot of stability assurance for an attack. But you do have a duty to do some level. So if you're attacking a client and you break something, you need to avoid breaking things rather. There's a growing kind of trend of attacking network devices and persisting on printers, which sounds fairly low stakes, compared to like a domain controller if you take a printer out. But if you attack a branch office that only has one printer and you brick it, then that's bad. You can have a bad time. The best example for this, and I was pleased I could find this example because it's a really good example, was back in the Arab Spring, and Syria was having there was a civil war. Lots of bad things were happening. There was demonstrations going on, protests, very bad. A lot of people were paying a lot of attention to Syria on the kind of the geopolitical world stage, all that stuff that's a few levels above my head. And then one day, Syria went offline. That's this big gap. So the whole country went down. And a lot of people on the internet, a lot of people were like, oh no, this is a terrible, horrible thing the Syrian government's doing. It's controlling the flow of information, all that stuff. And that's okay and fair enough. And that's the kind of view that we had for quite some time. But then a few years later, Edward Snowden burst on the scene and he revealed a large amount of interesting information. And one interesting little piece of information that I don't think, or that a lot of the people I talked to don't know about, and I found really interesting, was that wasn't actually what happened at all. TAO, a division of the NSA hackers, had attempted in 2012 to remotely install an exploit in one of the core routers at a major ISP in Syria, which was in the middle of a prolonged civil war. But something went wrong, and the router was bricked instead and rendered totally inoperable. And thus, Syria lost all connection to the internet. Like, wow, man. Like, next time I break something at work and I feel bad because I've taken like a client system offline, I'm just like, at least I didn't take a country offline, It could be worse. But the point is, we don't actually know what went wrong here. It could be that it was something completely out of control of the attackers. It could be a power failure. It could be that someone got paranoid and pulled the power plug. It could even be some weird detection mechanism that was in place. We don't know. But the point is that your attacks need to be stable. They need to be solid. They need to be reliable as much as is reasonable, I think. The third one that I've got here is detection techniques, and that's kind of an area where there's a lot of previous work done. It's also the area where I do a lot of work. So maybe that's why I think there's a lot of work done, because I see it. But for that section, I'm going to talk about kind of how we QA our detection mechanisms, how we ensure they're fairly stable at Countercept. So onward with my first war story, I guess. I'm not sure if it's a war story if it doesn't involve an actual adversary, but onward with my first story, which was the incident response scenario. So in this scenario, I was asked to write a detection routine for a code hiding technique. So there's a POC available online, so my task was simple. Grab the POC, write some detection. Great, fantastic. So I went away and I fired up volatility and I wrote a load of Python and I wrote this enormous script to detect it. And I ran it on my trusty laptop on my Windows 10 test machine. It ran, it detected it. I was like, fantastic, great. Messaged my boss like, oh, I got that thing done. Great, it was in record time, yay. And then just before I gave it to the IR team, and just before I posted it publicly on the blog, I thought, maybe I should test this on Windows 7. And it's a really good job I did, because it was broken horribly, right? It was broken horribly on Windows 7, and it was broken horribly on Windows 8, and it was broken horribly if I was a 32-bit machine instead of 64-bit, It worked on my machine, but nothing else. So it's a very good job I tested this. So the next few days were like, mad scramble getting all this working. But after this mad scramble, or during this mad scramble, I'm thinking, these stability problems are the same problems that real developers, I throw this term about real developers, I'm not offending anyone who is like a developer, I'm just using it fairly facetiously. There's entire people who are real developers who have spent their entire career addressing these problems. And it would be remiss if I was to ignore all of their progress and their work in the area. And not all of it applies to us, because fundamentally, as security researchers, we're solving different problems to software developers. So we don't have a lot of the problems they have, we don't have the same kind of life cycle, we don't have to push out patches depending on what we're doing. It depends, but there are lots of things that transfer between the two. And I thought this was a good example of something that would. So what I thought I'd do, I would automate some testing over different environments. So I've got my volatility script, I've got my POC, let's set up a load of different VMs and just test things. And I wanted to keep things simple here. So I wanted very simple detection tests. I wanted to run the POC, run volatility, and check that I got a yes, detection succeeded. That's all I wanted to do. I didn't want to do like false negative testing. I didn't want to do testing of capturing images in different ways. I wanted to keep things simple here. So I wanted to catch the scenarios where I would commit some code and forget to account for some weird APC format that's only in Windows 7 Service Pack 1. Yes, that happens. I also thought I'd tack on to the end, detecting breakage in my script due to updates. So a Windows update comes down, kernel data structure changes very slightly, everything breaks. I want to know about it before our client comes and says, here's a hard drive, can you analyze it? And we say, no. So I want to find out, and I want to fix it. Crucial step that I failed to mention there, I want to find it and fix it before the client comes with a hard drive and says, can you analyze this? So what we ended up with, a load of different VM images on different versions of Windows. Different versions of Windows, we did different service packs, different CPU architectures, different builds of Windows 10, that kind of thing. I didn't go any more granular than that, but I almost did. We download and build a POC on every test cycle, so that guards against the POC being fixed and changed, and make sure that we know if the POC changes and we don't detect it anymore. We deploy it, snapshot the VM, and throw that snapshot straight into volatility and just check that detection happens. So it's straightforward in terms of like testing. We're not testing, like we don't snapshot the VM without the POC and check that it isn't detected, for example. We don't do anything advanced or smart. We just do a fairly simple kind of test. It isn't intended to be comprehensive. And the reason I mention this is because it's very tempting and, or maybe it's just me, but it's very tempting to, once you start writing these tests, to write a whole load of like zillions of tests that test for every eventuality in any way that your code could fail. But you have to be very careful to kind of keep a lid on it and not kind of descend into the rabbit hole where net productivity kind of like drops off. My next example is the kind of cool, flashy ones of attack techniques. And I'm going to draw on I think I've got 2 or 3 examples for this. The first one was some very recent research into reflective loading, which, if you're not aware of reflective loading, it's an alternative method of loading code, which leaves less forensic artifacts. And I was doing some research into a particular reflective loading technique and how we can detect it in a very efficient manner. And I was like, okay, this is cool. I can apply the same kind of thing that we've done before. Yeah, I can make sure that the code runs. I can make sure that the reflective load completes successfully without breaking anything on a variety of different environments. So to achieve this, I just wrote some shell code that was just dead simple. The shell code literally just opens a socket, so it's like less code than a bind shell, you know. And then the test bench will just check connectivity. So fire up Windows 10, inject my reflective module, great, fantastic. And I wrote all this test bench, and I was a little bit dismayed, actually, I must admit, because the first time I ran it, everything passed. And I was like, it all works. Why did I bother writing all that test code, right? I was like, am I just wasting my time? But it turns out there was actually value that I got from this, and that it became very easy to generalize these tests and to adapt them once I had them running. So once I had my reflective loader going, and I can write payloads in assembler, then I was like, it'd be cool if I could write my payloads in C, for example. And then I was like, it'd be even cool if I could write them in C++. And it was very easy for me to extend my test bench to cover these cases. And it picks up all these tests, because like when you start going C++, it means you have to do some extra like extra work to make sure all of your static constructors are invoked and the CRT is enabled and all this stuff. And it helped me pick up and test that all these things was working. And because like after you make the investment of setting all this up, it's easy to tack on other bits that might fail or might not. So I wanted to build my payload with different compilers. And the reason for this isn't because I was going to use different compilers when I'm attacking things. It was more that one compiler might expose an edge case that would also show up under my regular tool chain if the stars align just right, then one day it would break on a client system. So that's the advantage there. We can flush out some bugs. We can also try other things that are less likely to cause problems, but we still just want to cover our back. So we start injecting into different processes, see if any of them cause trouble. Why not? If they do, then we can either fix them or we can add checks to make sure that no one tries to use that in production and break something. So yeah, the other two actually, that I had to check my boss before I put this in here because I wasn't entirely sure if I was allowed. But there was a time before I came to Singapore a long time ago, and I was writing a rootkit for an embedded device. So a piece of hardware. Come talk to me about it later if you're interested. It's a fun project. But it was just a research project, in case anyone's getting worried in the crowd, just a research project. And it's kind of interesting. I kind of wrote this thing, and I was like, OK, how can we test this? We've got the device. We can just check it runs. But I want to test things in a much more kind of fine-grained manner. So I set up Jenkins. This is Jenkins. If you don't know Jenkins, it's just a piece of software that just builds things and tests them. But it's very popular, and it's very generic, and you can plug it into most things. So most of this is powered by like a mixture of Python and Bash, Proper developers, real developers do it properly, but I don't. We've got a handful of tests for this rootkit. So at the bottom, I'm not sure if you can see it very well, but the point here is that there's a test that the actual embedded device has come up. So after I inject my rootkit into it, I want to make sure the thing hasn't failed to boot. I've got, at the top, you have to excuse my very casual naming conventions here, but at the top, I've got a test which will connect to the backdoor device and attempt to start some action. And then that passes or doesn't, depending on if I've got the code injection correct. There's an extra compress test, which tests that we can compress the firmware to make sure it fits into the real device's firmware on production, which is an extra layer. So if I get something wrong when I'm packaging the firmware, we'll know about it then. And then because I'm reusing the socket implementation that's on the embedded device, I've got tests for that elsewhere as well. It then becomes the next phase of this project, which I didn't get to, was to generalize and run these tests on many, many different variants of this embedded device. So yeah, fun project. The next one was another personal project. I had a research task, and I was like, oh, wouldn't it be cool? Go write a rootkit, it should be fun. So I wrote this Ring 0 rootkit. I was like, okay, this is a bit closer to traditional software development. There's probably a lot of stuff I can apply here. So I thought, what am I really trying to aim here? What am I really trying to assure here? And really my main worry was compatibility. One of the things that my rootkit did was it sat above the kernel, kind of, and it would intercept calls to disk access, as is fairly standard. And then when certain files were requested, it would just be like, oh no, they're not here, don't worry. These are not the droids you're looking for, kind of thing. So it's like basic file system stealth. So it's simple stuff. There's nothing like revolutionary about it. But I've seen a lot of people do it in ways that compromise system stability or that leave weird, that subtly change the way that the kernel API works and leaves the door open for detection. And the other thing, of course, I should say this was many years ago and things were a bit different then. We didn't have the huge prevalence of cloud antivirus and EDR wasn't quite as big. So the other thing I wanted to check was that I don't start hitting any heuristic, sorry, that should be heuristics, any heuristic engines which might pick up the fact that I'm modifying all this kernel memory. So once again, Jenkins, my go-to application for this kind of thing. I set this thing up, and you can see I've got builds in release and debug mode, and I've got 32-bit and 64-bit modes. And it's kind of small, but here I've got different entries for different versions of Windows. This is 32-bit Windows XP, in case you're wondering how long ago this was. I've got Vista as well, because, yeah. And then I've got different antiviruses that are installed. That's just an example, it doesn't have to be those. But the point is that I have VMs with different antiviruses installed, and I can boot the thing, and I can test things work, test I don't hit the heuristics, test that I don't break things horribly. Interesting project, it was fun. It also gives you this nice kind of matrixy thing as well. So here we can see these are some of the things I'm deploying on. Here's a state, and you can see here that everything that's on 64-bit is broken. So whatever I did before I ran this build broke 64-bit compatibility. So yeah, it was interesting, and it's yeah, a good step. And I don't know, maybe people do this and I just don't know about it, but yeah. That's all of my cool flashy attack techniques, I'm afraid. Now we're on to detection, which, as I say, is something that there is a lot of work that's been done in this area. And this is more of a kind of, more related to what we do at Countercept and how we detect things. So a lot of this is about the infrastructure we run and the way that we stop our clients from having problems with our detection mechanisms. So, as I say, we do this a lot. So I think this section of the talk was just me like asking other people in the company, you know, how does this happen, as opposed to personal projects. So a little bit of background into what we do at Countercept. We are a managed detection and response company, so we have a load of clients, we monitor their networks, and when people break in, we kick them out, or we alert the client, or whatever. And the way we do this is that we have a software agent that we install on every endpoint on every client. So the client comes, they've got 100 computers, okay, install your agent, great. We install the agent onto them all, and then the agent will run in the background and report a lot of events into this database, which is got a big database that takes a lot of data. So these are very verbose occurrences. So, for example, if you create a scheduled task, if you create a registry key that, you know, the registry key that gets evaluated to start something on boot, right? You start that, it'll be in this database. You start like, it's a very verbose database. So it's high quality data, but it's also very verbose. So we have then, the real value is in our team of eager threat hunters who are the people I work with, and their job is to comb through this database, think up hypotheses, think, what if someone tried doing such and such and such and such, and then search this database, find any problems, or find any instances where that's happening. So they might come to work on Monday thinking, oh, I've just seen this new attack on Twitter, let's have a comb through, make sure nothing's going on, that kind of thing. But the advantage is that we have these humans in the loop, and these humans are able to make a much more reliable and high-quality decision than an automated system. But obviously, a lot of attacks have a lot of commonality. So a lot of attacks will have some kind of persistence mechanism, some kind of module injection or code hiding or that kind of thing. And a lot of attacks will use off-the-shelf tooling as well. So because of that, we have also a rule-based automated detection system. And this system runs in real time and pulls this database and finds and matches events that it can notify that the threat hunters have occurred. So these aren't like absolute 100%, this is a baddie kind of thing. This is a kind of 90%, maybe you should check this out, you know, check this out kind of thing. But obviously the rules that this database, that this automated system runs on are very dynamic. Because of like the speed that our industry moves, our attacks are changing all the time, and our threat hunters are, you know, running 24/7 and protecting everyone is the corporate line for you. So because of this, we have this kind of list of kind of heuristic of hypotheses and rules that are applied to the database, and this gets edited, pretty much in real time by the threat hunters who will be pushing to this database. And this needs to keep the automated alerting running and keep it current. And we don't want to break it. Obviously, it goes without saying, I guess. But you can look at this diagram slightly differently. If you ignore, words I shouldn't be saying in front of a crowd, but if you ignore the clients, here, this tends to look a lot more like a traditional a traditional computer science kind of problem, right? You've got a user base, you've got shared code in this rule set itself, and you've got an application that you want to maintain. So from there, we can note these similarities and we can apply all the traditional software development methodologies. The first one, which is, this might be a bit obvious for some of you, bear with me. First one is that you should use, sorry, wrong slide. You wouldn't think that I've been rehearsing this madly for the last few days, would you? Sorry. There is a shared code base, as I say, of attack hypotheses, and that's the part that we want to QA. That's what we need to ensure stability of. There are some differences between the between this flow and between the traditional software development. And I want to highlight this because one common pitfall is to think that you can apply or think that you should apply all of the traditional software development workflow into your work. And that isn't often the case, usually isn't the case, right? And there's a lot of situations where you can make your work a lot worse by trying to do this. I think, I'll give some examples as we go forward. So it's important to note the differences between these two problems. First one, the time required to deploy new rules really is crucial. If we see a new attack and we want to get alerts about it, we can't wait for, we can't push our rules out and then wait for them to go through a huge QA process, and a month later we roll out our new release and then we can detect all the attacks that were in use 2 months ago. That'll be no good, right? The other thing that sounds kind of counterintuitive is that some downtime in this alerting system is actually acceptable to us. Because as long as this downtime is short and we can roll back, the database itself is still getting events from the client. So the alerts will still fire when it comes back up. The other thing I should mention, we do have a dedicated team who look after the database and look after the agents, and that's separate. But as long as we can roll back to it, a short downtime of, say, 3 or 4 minutes is totally okay to us. The worst case just becomes that we don't spot an active attacker for an extra 3 minutes, which is, not the end of the world. It's acceptable, I think, is the word. As I say, we won't miss the alerts during the downtime. So we can apply the usual development flow to this. We use Git for keeping our rule set. It may seem very obvious, but I do see a lot of security researchers who would benefit from source control who don't use it. So this is one thing I do use very religiously. Stick your rules in Git, makes things a lot easier, makes it easier to roll back, makes it easier to do most things pretty much, as would any real software development practice. Our hunters will push their rules into the staging branch, so they'll go to Twitter or go to a super duper threat intel feed, which isn't Twitter, and then find some new attack, use that to make a rule, generate some hypotheses, commit that to the staging branch. From there, the server, so the centralized server itself, will immediately then pick up the change and do some very basic testing. So it'll check the syntax. The rules are just in YAML, so it'll make sure everything's okay there. It'll do some very basic true, false, negative testing. So, for example, this is an example rule, by the way. This isn't one of our production rules. But here we've got a rule to detect mimikatz with these particular arguments. And we're saying that if we see this situation occur, mimikatz runs with these arguments, then we need to fire. And we should never fire if we see a rule with, you see that this is an N. I'm sorry, I really want to tell the person off who wrote this rule, but he's really good at his job and he does loads of software development, so I'm not entirely sure I'm brave enough. I do note the presentation is being filmed, so maybe I'll just send him it and it'll be my passive-aggressive deed for the day. But anyway, it shouldn't trigger on a different process. So it's very basic testing. So there's no firing of mimikatz. We don't launch mimikatz. We just test very basic stuff here at this point. And because we're only testing something very basic, we can get this push and this test going in less than 5 seconds. So from a hunter hitting the button to push to it being in staging. So it's a lot less than the time developing the rule, and it's not something that our hunters have to worry about. From there, if it's a particularly urgent rule, so for example, if we've got a malware infestation on a client estate, there's 10,000 computers, we're pretty sure that lots of them are infected, someone's written a rule that's going to detect the infestation, we need to get it out as soon as we possibly can. Then we can merge it into the live environment immediately. Because we're not too worried about short downtime, we can, the actual flow here is that another hunter will go and QA it and be like, oh yeah, looks fine, let's go. Merge it in, see what happens. If it breaks, roll back. It's not the end of the world. It's not good, it's not the end of the world. So yeah, that's not our usual workflow. We don't usually merge to live immediately. Normally we go through a different system, and this is a screenshot of that system. It's called Watchtower. And this system runs periodically and will actually perform the attacks. So, for example, here's a rule to disable Windows Defender. So in this attack, when the relevant rule is changed, or when there's a commit to Git, this system will go fire up a VM, run a script, PowerShell one-liner, that will disable Windows Defender. And it will monitor the alerts generated and make sure that there's an event generated that tells us that situation has occurred. So obviously this takes a little bit longer, And because of this, it's you can see the times that each test took here. This one took quite a long time, almost 9 minutes. So because of that, it doesn't run on each check-in, but it runs periodically and makes sure that we don't commit anything that causes a major regression in kind of detection. If we were to push something and then find out that we'd typoed something and we lost all the rules, then that would be terrible. Yeah, I did that in a previous job because I was using a tool called LogWatch to monitor my syslog entries, and it functions with a set of regular expressions that you can use to whitelist things you don't want to know about. And I left, what was it? I think I put a space in the wrong place. Oh, that was it. It was that if you had a blank line in the configuration file, it would use that as a regular expression that would match everything, and then you wouldn't see any more rules anymore. So yeah, that was a bad day. But anyway, I digress. At least I didn't take an entire country offline, right? I digress. So yeah, in summary, that's all the cool stories I have for you, or the hopefully cool stories I have for you. In summary, TLDR, some of these tools used by real developers are very useful to us too. They can be used to enhance the stability of your work. They can be used to enhance to give you a stronger assurance that they do what you think they will. One thing I do want to mention here is a story of, or not story, but one consideration you should take into account is how long you want to maintain your tools for. So in my role, I'm supposed to write a lot of blog posts. So I'll write a big blog post, I'll write some code, put the code on Git, put the blog post up, I'll make sure it all works, fantastic. But I also set up this continuous testing so that if something happens and my code no longer works, so if there's a Windows update, for example, and it breaks my code, I want to go back and I want to fix it, and I want to make sure my blog post is reasonably updated. And it's only worth doing this kind of testing if you're willing to do that and if that's a business priority for you. So this isn't really a technical question so much as a business question of how long you want to support your blog posts for or your output for. So it's important to kind of pay attention to these things and make sure you don't find yourself thinking, oh, this is a cool feature, now we'll know when it breaks, if you're not interested in actually fixing it when it happens. Which leads into the next point, which is not all of these tools are useful to us, and you can cause major problems if you try to apply them blindly. I think it would be a worst case scenario if everyone went away from my talk thinking that I was saying software development practices are great and hackers don't know how to use them, because that's not what I'm saying at all. I'm saying some of them are good, some of them can be used. I think we should look more into using them, but I think we do need to be cautious. It's not worth, like, if you're a red teamer and you have an exploit for a target for your client system and you're never going to see the client system again because it's a totally bespoke system, then there's not really much point in QAing it over 10 different processor architectures, right? Just that kind of thing. The main takeaway or the main use that I got from this workflow was the testing over multiple environments. It takes a very long time for me to spin up a load 10 VMs and test on each one. And to be honest, everyone's got better things to do with their time than that. So having a script that will do this all for you is fantastic and very, very useful and really enhance the quality of the stuff that I'm writing. This is very applicable to OSs. You want to check on lots of different OSs, patch levels, that kind of thing. It's also very useful for POCs. So if you have a POC and then your attack POC, you make your POC, you're like, great, it works, fantastic. Then the next day you're in the shower and you think, I wonder what happens if I allocate memory by using this in an API call instead of this one. It needs to be very easy for you to go to work the next day, spend half an hour implementing that change, because if you need to spend a whole day implementing that change, it might not be something you can fit into your workflow. So yeah, it opens it off, that kind of thing. And also deployment parameters. And what I really mean by this is stuff like injecting into different processes. You can just start to play around and just do things and see what breaks, see if anything breaks. Find the breakage, write some checks in your POC or fix it or something like that. It isn't free in terms of effort. Nothing's free, I guess. I guess we all know that. You do need time and effort to set up and maintain it. You might have to, install Jenkins, you have to write your tests, you need to keep your tests current. So it does take time and it does take effort. It's worth thinking, as I say, about project lifetime and how much effort you're willing to invest. What's going to happen if someone else needs to take over this project? Is it going to be practical? If not, why not? And it may require extra resources, which Yeah, so you might have to buy a new server, you might spin up some new VMs, you might need some more software licenses. This is stuff that your software guys, if you have a software team, this is stuff they may already have and they can probably help you out with. They can probably point you in the right direction, and if not, I don't know, shout at them. Anyway, yes, I digress. I probably shouldn't tell you to shout at your co-workers, so ignoring that. That's all I have for you today, so I hope you found it interesting. I know it's a bit of a divergence from the kind of talks I normally give. If anyone's got any questions, come and grab me later. I love talking about computers, and I never shut up about them. Or come and ask me now if you want.
Is there any question? Is there any question for our speaker?
Okay, fair enough. It's either very good, because everyone understands perfectly, or very bad, because no one has any idea what I'm talking about. One of the two.
Can you give them a few minutes to process first?
Perfect time to drink Red Bull.
I hear some mumbling around, but you don't dare to voice out to you.
No questions? Sure. Maybe I shouldn't have said I'll answer them later. Maybe I should have just said I will not answer your questions unless you ask them right now. No? Oh, fantastic. Excellent.
I just can't do it. Sorry. Okay, so it's about the last slide, about the cost, the time cost. How do you, WRFC here, how do you decide what's worth it to put in the amount of time to write a blog post to update it? Like what type of exploit or what type of research or what is worth the time that you put in to do this type of work?
Tricky question. Thank you for asking the question. Appreciate it, even if it's a hard question. But yeah, so the question is, how do you decide how much time to put into these kind of things? And it is like a tricky question, and it is driven partly by what you're trying to achieve. So if your aim is to drop a blog post and get lots of hits in a short period of time, yeah. But if you want to drop your blog post and you want something that you can refer to in the future, it's powerful to go to a client and be able to say, oh yes, that attack has some similarities to this attack we saw 3 years ago. And it's not the same, but it's kind of similar. It kind of gives the client the impression that you're doing it right. I don't have a solid answer for you, I'm afraid. I mean, actually, yes, I do. Kind of. In that, so because at Countercept we have this monitoring system, and we can find out stuff about the client operating systems. So one thing we can do is pull down a big list of what operating system everyone is on. So one thing I did with the incident response plugin was I was able to make a big graph of what everyone's using and know where to focus my efforts. So increased telemetry, or some amount of telemetry, is very helpful there. Like I didn't expect about, I think it was 40-50% of our client systems were 32-bit installs of Windows, which really surprised me. So it's a half answer. I hope it sates your curiosity. Any other questions now that the first question's been asked? Oh yes, I'll do that. I'll take another one. Yes.
When you release attack tools specifically, how does the firm decide? I guess almost like the PR line, if they're used by bad guys. So for example, some really cool tools by some South African outfit were used by Iran to attack, say, the UK or America. And obviously the media likes to say you are building tools for the bad guys,
Sure.
which isn't the case. How do you manage internally what is worth it to put out, and then how do you manage the media on the outside? Because often we get a blanket don't release tools if they might be used by bad guys.
It's, yeah, again, it's a tricky one. Slightly less tricky than the previous question, but slightly tricky. It's actually, I've got good examples of that because the personal projects, one of the personal projects I mentioned there, I thought was very interesting, the embedded thing. I thought this is a very interesting project. Maybe we can put it on the blog at work. And I talked to the people at work and they're like, well, can't really see any good use for that. I don't think it proves any real point other than that bad guys can do bad. So I was like, okay, fair enough, ho-hum. Yeah, I think the team has a kind of group decision, I think, and I think we have the people who see things in a purely technical manner kind of working very well with the people who are more kind of objective based in terms of PR. we had an incident. We had a situation a few months ago where there was a high-profile public malware that targeted a list of MAC addresses, and we decrypted this list of MAC addresses, and there was a lot of debate internally over whether we should release it or not. And we decided not to because we decided not to because we didn't want to lose the goodwill of the original researcher. We didn't want to cause any problems with that. And what we did do is we were able to look at the value that doing that would give. So in that instance, the original researcher, Kaspersky, had an online checker, and you could submit your MAC address to see if you were targeted. But there were some people who were unwilling to submit their MAC addresses. So we were like, oh, if we release this list, people can check it without using the site, but not sure we should. So we ended up they also released, slightly roundabout answer, but Kaspersky also released a binary that would check your MAC addresses, but you'd have to run it on your computer. And some people were like, don't want to run this closed source binary. So we pulled the encrypted hashes out of that binary, wrapped them in a Python script so people could, so some people were a lot happier about running that rather than running the binary, but avoided giving out this big list of MAC addresses, which would have upset Kaspersky, which was good because I was talking at their conference a week later. So I'm glad we didn't upset them. So yeah, I'm sorry, I kind of answered a slightly related question rather than the actual question, but it is a team decision that requires, I think, a lot of different viewpoints from different parts of the company. So I think, I don't know, maybe the key point there is kind of open and frank communication over the objectives you need. Any more? Okay, no more questions. Fantastic. Hope you enjoyed it.